Moving on to the next section, we're talking about chemical reactions in this chapter. And so we'll start with talking about chemical reactions that occur inside a solution. Now, this is the way in which most reactions occur. They occur in water. Two chemicals present in water react, and water is just kind of the what would we call it? I guess the carrier for these chemicals, just giving them a place to react, a place where it's really easy for them to move around, unlike if they were on their own in the solid form. So to start off, let's just talk about solutions in general. So a solution is a homogeneous mixture of a solvent and a solute. A solvent is the one that you have more of, and the solute is the one that you have less of. I'm not really sure why, but the terms solute and solvent always remind me of this analogy, and that is that when you have some loot, you need to put it in the vent to hide it. So think of like if you have loot at your house, maybe you have like a lot of cash that you're saving up and you don't want anyone to be able to get to it, you put it in this vent, and they actually have these secret hidden compartment vents. But I always think about a robber like with a bag of cash on his back, and he's robbing a bank and he needs somewhere to hide it real quick, and he opens like one of those really big air vents and throws it in. Completely random, but the idea is that you have this loot, solute, that's the smaller part, and you put it into the vent, the solvent. Okay, so sorry for the weird analogy, but maybe that will help you remember. So the solvent is just the more, and the loot is the one you have less. A lot of times water is our solvent, and so we'll have a large amount of water and then we'll add some substance to it. And those solutions are called aqueous. And we'll deal with those a lot in chemistry because, like I said, we have a lot of reactions occurring in water. So if you see AQ or aqueous, that just means that we have some chemical and it's in water as its solvent. When water is the solvent, water is not usually involved in the reaction. It's just giving the reaction a place where it can take place. Alright, some more terminology. An electrolytic solution is a solution that can conduct electricity. Electrolytic, electrical conducting. These solutions occur whenever you have an ionic compound dissolved in a polar solvent. And water is polar, and it's normally going to be our solvent. So anytime you have an ionic compound that's dissolved in water, that is going to create a solution that would then conduct electricity. Electricity is the movement of charge. So ions are charged species, and if they're in water, they can then move, unlike in the solid form. Remember when we were talking about compounds, in the solid form, those positive and negative ions are locked into the lattice. But if we put them in water, they can then move, and that solution can then conduct electricity. The electrolytes, as they're called, or the ions, are what are conducting the electricity. And the more ions that we have, the better able the solution is to conduct electricity. For example, if we place sodium chloride in water in its solid form, it will break apart into sodium plus ions and chloride minus ions. And notice how we're denoting this. The S is telling us that it's a solid, while the AQ is then telling us that it is dissolved in water, with water being the solvent. When this occurs, it's very important, if you were asked to write this, you would want to make sure you included the charges. Because in the compound, those charges cancel. But when it breaks up into the ions, they're then separated in the solution. And sodium with a charge is very different from sodium without a charge. So we want to make sure we include those charges on our ions. This is what the ions would then look like in the water if we could zoom in. You see the water is turned or oriented around the ions in a very specific way. So the oxygen end of water is turned toward the sodium because the opposites attract, and then the hydrogen end of water is turned toward the chloride because again the opposites attract. Notice the number is somewhat different. It looks like there's more water trying to get around sodium than around the chloride. There's really not a big deal there. We may get into that a little more. However, the size is critical. So when we're drawing this, which you'll be asked to draw a lot on the AP exam and kind of interpret these drawings, notice how much bigger the chloride is than the sodium. If we look on the periodic table, sodium is to the left and chloride to the right. And according to our trends, they should get smaller as you move across. So chlorine should be smaller than sodium. But what has happened here is sodium has lost an electron. So it took it back a whole energy level, while chloride gained an electron, and that made it much larger. So your anion is going to be larger than your cation because the cation lost the electrons, the anion gained. So keep that in mind when you look at these drawings. If it gains an electron, it should be larger than the one that lost the electron. If the ion is smaller, like here we're comparing two that both have a positive charge. If an ion is smaller, that smaller ion is going to have a stronger electrical field. Remember, think about Coulomb's law, right? Coulomb's law has that distance or that radius on the bottom, d squared. And so in a smaller ion, the waters can pack in closer, so the attractive force would be stronger, so they're going to drag more water molecules along with them. So notice if we look at the lithium compared to the cesium, the lithium, even though it's smaller, it's going to have so many more water molecules packed around it that that's going to slow down its velocity in terms of ion movement. The cesium, not as many waters are going to pack around it, even though it's bigger, because the distance is going to be greater, so it's going to have less attractive force to pull in those water molecules. So again, Coulomb's law is coming into play. Smaller ions, stronger attractive force because those water molecules can get closer to that nucleus and kind of hold on to the ion. All right, what about molecular compounds in water? These are covalent. Okay, when we say molecular, covalent. Most of these are non-electrolytes, meaning they may dissolve in the water, but they do not dissociate. So to dissociate in water means to form those ions, like we saw sodium and chloride doing. Most covalent compounds are not going to do that, so they're not going to conduct electricity. For example, sugar, water, if we mix methanol and water, those are going to be non-electrolyte solutions. They're not conducting electricity. However, we have a few covalent compounds that are electrolytes, and they may be weak or strong depending on what type of acid they are. So a weak acid, that's a compound that's going to have a hydrogen that can come off. A weak acid is going to partially dissociate, usually 10% or less. So that's why we have this double arrow here. A little bit of it is going to form the products, but most of it is going to stay reactants as it dissociates. So we'll get a few ions out of that, and so we'll have some low conductivity. However, if we have something called a strong acid, like hydrochloric acid is a strong acid, those acids completely dissociate in water. They completely break apart, and so we get lots of ions from those, and they have high conductivity. It's kind of backwards in the thinking, but a weak acid holds together, while a strong acid completely dissociates, and the reason we call it a strong acid is because it's really good at giving off its hydrogen ions, and a hydrogen ion is what makes an acid an acid. So most covalent compounds do not conduct electricity in water, but a few, if they are acids, they may, and they could be strong acids, which means they would be a strong electrolyte, like an ionic compound, or a weak electrolyte. When things dissolve in water, like covalent compounds, if they are nonpolar, they're more likely to dissolve in a nonpolar solvent. So if you're mixing a solute and a solvent, if you have a nonpolar solute, it's more likely to mix with a nonpolar solvent. For example, oil is fairly nonpolar, and if you try to put it in water, which is polar, those are not likely to mix, right? Oil and water don't mix. But if you have two things that are polar, like water and methanol, then those can mix well. And the reason is because water already has this positive negative region because it's polar. So if you put something else in there with a positive negative region, then the positive and negative regions can be attracted to each other. But if you put something in there like sugar that doesn't really have those positive and negative regions, then there's nothing for the water to be attracted to, and so excuse me, not sugar, but oil. There's nothing really for the water to be attracted to, and so the water will kind of stick to itself and leave the oil out. Okay, think of it like Mean Girls, right? They kind of circle around themselves and then no one else can get in the circle. That's kind of the way water acts unless there's someone like it coming into the mix. All right, we're going to start talking about precipitation reactions. A precipitation reaction is a reaction in which you have oppositely charged ions. So let's go here. We've got oppositely charged ions in the reaction, and they're going to stick together. And the force of attraction between them is greater than the attraction to them in the water. So in a precipitation reaction, what you have happening is two oppositely charged ions kind of find each other in the water, and their attraction to each other is greater than the attraction between them and the water, so they're going to stick together and form a solid. We said earlier that ionic compounds in water break apart and the water surrounds the ions, and that is true unless those ions are more attracted to each other than to the water, and then they'll find each other and they'll make a solid. So how do we deal with these precipitation reactions? Well, first, before we look at an example, I want to look at a picture of what's happening, okay? And then we'll come into what we would do in terms of writing them. Alright, so in this animation, we're going to have sodium nitrate, which you'll see with the yellow dot, and then the nitrates, the blue and the red, and calcium carbonate. All of these ions are going to be in solution, and then you'll see your water molecule. Alright, so to start off, all the ions are in there because sodium nitrate, calcium carbonate, okay, they've dissolved in the water. You see them just all kind of mixing. And they kind of paused it there. You can see the different ions in the solution still. What's going to happen here is some of the positive and negative will start to kind of stick together, you see, and then they'll just break right apart because the attraction to the water is greater. However, there's a combination here that if they stick together, their attraction to each other is greater than the attraction to water. And that is between the calcium and the carbonate. See that? Whenever they find each other, their attraction to each other is greater than the attraction to water. So they'll stick together, and more calcium and carbonates will continue to stick together until you have this large clump of calcium carbonate, which is our solid that has formed, and that is called your precipitate. So in a precipitation reaction, you have ions, so you're going to have ionic compounds in these types of reactions, and then you'll have two ions that are more attracted to each other than to water. Now, how do you know that they're more attracted to each other than water? There's some rules of solubility, and in those rules, it'll tell us which ones are going to form a precipitate and which ones are more attracted to water that'll stay in the solution. So based on those rules, we can kind of predict whether a solid will form or whether the ions are just going to stay in the solution. But if we think back to Coulomb's law, calcium carbonate, makes sense as a precipitate because you got a +2 and a -2. So those big charges are going to create a strong attractive force, and so those are going to come together. Remember, water, it only has a partial positive and a partial negative charge. So let's look at an example. Here they want us to write what is called a net ionic equation. So we're going to learn how to do that in this section. We want to show the reactants and the products. And what are we mixing? We're mixing an aqueous solution of barium nitrate. That just means it's in water. The water's not involved, but the water is giving it a place to react. And an aqueous solution of sodium sulfate. So our main reactants are barium nitrate and sodium sulfate. So here is our initial reaction. Here's barium nitrate and sodium sulfate. And it said that they were both aqueous, or both in water, and they are both soluble. That word aqueous kind of cues us into the fact that they're both soluble in water. So the barium nitrate in water is going to be in the form of ions. So barium +2 ion, and then 2 of the nitrates to balance with the +2 from barium. And then the sodium sulfate was also aqueous, so we're going to have 2 sodium ions and a sulfate ion. And the reason we have 2 sodium ions is because it's only +1, so we need 2 of them to balance with the sulfate, which is -2. So all those ions are floating around in the water to start off. So we're going to make those our reactants. Now, there's kind of 2 ways to write this. This initial way is what is called your molecular equation, and it's just showing everything stuck together. And then what we're showing in the next step is what is called your ionic equation. It shows things as they really are, because we know in the water the barium and the nitrate are not stuck together. They are in the form of ions. So you see that we've broken them apart and shown that, and the same thing for your sodium sulfate. But let's talk about when they all get in the water together, what happens? Well, the barium and the sulfate are going to find each other, because the barium and the sulfate with that +2 -2 charge, they're actually more attracted to each other than the water. So they're finding each other and sticking together to form barium sulfate solid. But the nitrate and the sodium, they're still just floating around in the water. So we still have 2 nitrate ions and 2 sodium ions on our product side. What we're going to do is simplify this by taking out the nitrate and the sodium, because in the beginning they were dissolved in the water, and in the end they're still dissolved in the water. They didn't really change over the course of this reaction, so we call those spectators. So all we have left is the fact that the barium +2 was floating around in the water, and so was the sulfate -2, and they found each other and formed barium solid. And that is basically what happened in the reaction. The sodium and the nitrate were not involved. So we call those spectators. And then what you have left is called the net ionic equation. The net ionic just shows what happened overall. It's like your net income. That's after the taxes are taken out and everything. What is left? What do you actually get to spend? That's what the net ionic equation shows us. What actually happened. Don't tell me about all the other stuff that happened in between with the sodium floating in the water. Just what happened. Barium ions and sulfate ions got together and made barium sulfate. Net ionic equation. We use net ionic equations for reactions that occur in water because we have some ions that don't participate, and we don't want to include those because they're not participating. They're just floating around in the water. So a net ionic equation shows only the reaction that took place, while the complete ionic just shows all the species that are present. Notice on the left-hand side in the complete ionic, you have barium nitrate listed as aqueous. So that tells you that it's just all ions in water. and sodium sulfate also listed as aqueous, and sodium nitrate listed as aqueous, but your barium sulfate is listed as a solid because barium sulfate is not soluble in water. The barium and the sulfate are going to stick together because they're more attracted to each other than they are to the water. So the sodium and the nitrate are aqueous on both sides. That's kind of how you spot a spectator. But the barium and the sulfate are not aqueous as reactants and products. They're aqueous as reactants and then not as products. Alright, so how do you know if something is going to dissolve in water or not? How do you know if it's going to be more attracted to the water or more attracted to each other? These are the rules that you need to know. The first rule is if it is a salt, that means it's ionic. Okay, note that. Salt and ionic. We're going to use those as synonyms. So if it is a salt or if it is ionic and it has sodium, potassium, ammonium, or nitrate, those are going to be considered to be soluble. I'm going to modify this a little bit. These two are from group 1. So we're just going to say if it has an ion from group 1 or ammonium or nitrate in it, we're going to say that those are always soluble. So if we see those, we know those break apart in water. Those things are more attracted to water than whatever else they could be joined with, so those compounds that contain those will dissolve. Alright, let's do one more example of this together. Okay, so we have an aqueous solution of lead 2 nitrate and sodium iodide are mixed in a beaker. So our reactants are lead nitrate and it's lead 2 nitrate. That means it has a +2 charge, so we need 2 nitrates to go with it, and sodium iodide. So these are 2 ionic compounds and both of them are aqueous. I know that because nitrate is always soluble and sodium is always soluble. So I put aqueous as my subscript on both of those. For sodium iodide, both of those have a 1 charge, so it's just NaI. Whenever you have 2 ionic compounds that you're mixing together, this is going to be a double replacement reaction. So the lead and the iodide are going to form a compound, and the sodium and the nitrate are going to form a compound. The lead has a +2 charge, so that's going to be PbI2, and then the sodium and the nitrate both have 1 as their charge, so NaNO3. The PbI2 is not soluble. The attraction between the lead and the iodide is greater than its attraction to water. The sodium nitrate is soluble, and I know that because my rule said that sodium is always soluble and nitrate's always soluble. So either way you look at it, that's soluble. But lead iodide is not. So I put a solid in parentheses as my subscript there. Notice I've balanced this equation as well to make sure that I have the same number of atoms on both sides. Now, let's see if we can figure out the net ionic reaction. So lead nitrate is soluble, so that'll break down into its ions, lead +2 and nitrate -1. So this is going to break into 2 ions. This sodium iodide is soluble, so it'll break into its ions, sodium +1 and iodide -1. This is staying together because it's a solid. And this sodium nitrate would break apart into its ions. So I'm going to have lead +2 and 2. That subscript's going to come out. I'm going to have 2 of my NO3s with a negative charge. Now this this coefficient in front of the sodium iodide is going to give me 2 sodiums with a positive charge and 2 iodines. Whenever anything breaks apart in water, we're getting these ions, these charges. Now that lead iodide is going to stay together, and then we're going to have 2 of our sodium ions and 2 nitrate ions. Sorry, it's hard to write with this marker on the videos. Alright, so you can see here that the lead was +2 on the left, and then it's in the lead iodide on the right. The two nitrates are soluble or aqueous on both sides. So those are canceling as spectators, and so are the sodiums. They were aqueous on both sides, so they're canceling as spectators. So that leaves me with the lead +2 and the two iodides combining to make lead iodide solid. Okay, so I'm going to erase this. And then you can see there the net ionic equation. All right, that's where we'll stop for today, and then we'll pick up talking about redox reactions.